Hey guys, how's it going? This is the first physics module, and it's presented by Spencer Sabatino, my partner, and Will Cotter, that's myself. And so, in this video, we're going to be talking about unit consistency and dimensional analysis. We'll be talking about significant figure rules without operations. Then we'll get our way to scientific notation, and finally we'll end off with significant figure rules with operations. And so with that being said, it's a general note that all references and materials used are mentioned below in the comments, and absolutely great resources, so I would definitely recommend checking those out. That being said, let's make our way to dimensional analysis and unit consistency. And so those are a couple of really long words, but what they mean is very simple at its core. And so basically, we want to make sure that when we are going from one unit to another, we are converting with correct conversion factors in order to do so. And we do this every day. For example, if I were to have 6 donuts that I were to bring home, those 6 donuts could be a half dozen, because we know that per 12 donuts, we have 1 dozen. And therefore, we can say 6 divided by 12 of a dozen, and that's a half dozen. So you're already familiar with the idea of dimensional analysis, and that is just using conversion factors to be able to convert between one unit to another. And so it's important when we go on this road to be able to realize a few different things. The first thing is that we have to have a roadmap of how to get from point A to point B. And with that being said, I might have a problem where I have to convert between one thing and another, and I might not know how directly to get there, but I may know how indirectly to get there. So, for example, off the top of my head, I don't know how you would convert meters into miles, but I could figure out how to convert meters to centimeters. And knowing the 2.54 centimeters makes 1 inch, and that just comes from a lot of repetition, if I knew this right here, this conversion, then I could figure out that however many inches, there's 12 inches in 1 foot, and then I can convert from feet into 1 mile, and therefore I would go from meters to a mile. So, for example, if I were to have, let's say 3 meters, then what I would do is I would say, well, in 1 meter, there's 100 centimeters, and therefore these units cancel out. Then I want to say that in 2.54 centimeters, I have 1 inch, and then centimeters cancel out. And then in 12 inches, I have 1 foot, where inches cancel out. And then finally, in 5,280 feet, I have 1 mile, and then feet can cancel out, and we're left with miles. So all that's left to do is just to multiply on top. So I would basically say that 3 times 100 times, 1 times 1, but you don't have to write that necessarily, over 2.54 times 12 times 5,280 would give us however many miles. So, X miles. And I'm not going to do that right now because I don't think that's a great use of my time. But with that being said, that's how you would go about it. You could just plug that into a calculator. So you could plug this bad boy into a calculator. With that being said, it is possible to use this method to go from one measure to another. So, for example, I could go from a displacement or distance to a time. But the only way to do that is to be able to have a proper conversion factor. So in this case, I would need a velocity. For example, I could say if I moved 3 meters and I wanted to figure out how many seconds I did that, well, I would need to know how fast I was going. I would need to know my speed. So if I said I was moved 3 meters and I was moving at, let's say I was moving at 3 meters per second. Well, it would be pretty simple that it would be 1 second. However, we could say then that in 3 meters, there is 1 second. And vice versa. If I had an amount of seconds, so in this case, we would have 1 second. But vice versa, and I'm kind of running out of space for this slide right here, but if I were to have 2 seconds in this case, and I was moving 3 meters per second, so there would be 1 second, 3 meters. We'd have to make sure these seconds cancel out, and we would know that I would move 6 meters in that time. So it's really important here just to make sure that we have a roadmap of where to go, and it's important to make sure that we're being consistent with our units throughout. In other words, I'm making sure that I can be able to cross off a unit before I move on to another one. Alright, with that being said, let's move on to significant figure rules without operations. So the idea of a significant figure is that we're able to display numbers to an we're able to display numbers accurately as we're able to measure them in lab or other applications. And so with that being said, the rules for finding out however many significant figures there are in a number are as follows. First off, all non-zero digits are significant. And I'll change the color real quick. But all non-zero digits are significant. And basically what I'm able to figure out through that is that if I was given, let's say, 5.5302, let's just say 5.532 for right now. Well, in this case, all 4 digits of this number are non-zeros, and therefore we have 4 significant figures. So even as we have zeros in a number, we know that all the ones that are non-zeros are going to be significant. And that's the first thing to keep in mind. The next thing is that if we have any zeros placed in between, so let's bring back that number that I was talking about, 5.5302. In this case, well, we would have to realize that, again, these 4 digits are significant. However, this 0 is also significant because it is between 2 non-zero digits. And therefore, we have 5 significant figures. Next thing to realize is that all zeros trailing significant figures to the right of a decimal point are significant. So in other words, if I was given, let's say, 0.201000. Well, in this case, the first thing that we should do is apply Rule 1 and realize that we have a 2 and a 1. So the 2 and the 1 are both significant. And then we have a 0 in between them, as we talked about in Rule 2. So we have 3 significant figures off the bat. However, we know that we have 4 zeros that are after a decimal point and that trail the non-zeros, and therefore we have 7 significant figures. Every single one of these digits are significant. However, if we were to write, instead of this, 0.201000, and just basically introducing this 0 digit, well, we would realize that it's, 1, not trailing, and it's also the main key point here about this 0, so this 0 is that it is to the left of a decimal point, and therefore it is not significant. So we would still have 7 significant figures. Alright, and so just as a general discussion before we move on to the idea of scientific notation, the rules for determining significant figures we just went over. However, in practice, a rightmost digit is frequently called the digit of uncertainty. And in chemistry, you'll come across that a lot. And in physics as well. And what that means is that we often have to interpolate that, and therefore we are uncertain if it's actually what it is, but it's close, and therefore it is the last digit that we show. So basically, let's take this test tube that I've drawn, and we can see that the meniscus over here it's between 10 and 20, and it lies a little bit closer to the 20. And based off the eye test, I would say a value of 17 or 16, let's say this is in milliliters, might be a good guess. So either one of these numbers would be a good guess. And you can see how we're not certain if it's a 6 or 7, hence the name, the digit of uncertainty. So, as we move on to scientific notation, the idea behind this is that sometimes we are working with infinitesimally small numbers or infinitely large ones. And not large as in 500, but large as in 500 billion, or numbers like that, or small as in 0.0000000, and on with zeros. And so the idea here is that we want to condense those numbers for readability. And the same can be said, again, with large and small. But the rules for scientific notation are as follows. So 1, we want to locate the leftmost non-zero digit. So let me explain. Let me give you an example. So let's say 0.000002305. Well, the leftmost non-zero digit would be 2. So it would be this, It would be this 2. So we have located that. Now we move on to step 2. Now we count the decimal places it takes to move the decimal to the right of that digit. So if we bring this down, I'll copy it. Now what we want to do is we want to count the decimal places. So 1, 2, 3, 4, 5, 6. So 6 to the right. 6 to the right. And so with that being said, bring it on down to 3, we display with the correct orders of 10. So in this case, we would have to realize that if we move we still want to be mathematically accurate and consistent. So if we move the decimal point here to 2.305, we need to multiply by 10 and negative 6 orders of 10. And therefore, this is called scientific notation. And that right there is scientific notation. However, in step 4, we want to use the correct significant figures to be sure that we're showing the same number. And so in this case, we do have the correct significant figures because we can see that, well, based off of what we just learned in 0.000002305, we know that non-zero digits are significant, so we have 3 of those, and then we have a 0 in between them. And then these zeros are to the left of the first non-zero digit, and they are not trailing but leading, and therefore they are not significant. So we have 4 significant figures that are at play. And once we bring down 2.305 times 10 to the negative 6th, well, we just apply the same rules, say that these 3 are significant because they're non-zeros, the zeros in between them. So we have, again, 4 significant figures. They match, and we are happy with that. So just to review on that, we want to locate the leftmost non-zero digit. We want to count the decimal places it takes to move the decimal to the right of that digit. We want to display with the correct orders of 10, and then we want to use correct significant figures. So this is a good example as well. If I were to, and I'm going to go very quickly through this, but if I were to have 2,300,000, in this case, I would realize that although we don't show it generally, the decimal point is placed right here. So what we can do is we can move this decimal point to, and find the, we first find the leftmost non-zero digit. And so once we have that 2, this 2 right here, we want to put the decimal point to the right of that digit, and that is rule 2. So 1, 2, 3, 4, 5, 6. So we have 2.3 times, let's say 2.30000 times 10 to the negative 6th times 10 to the 6th. So that is rule 3. Display with the correct orders of 10. Well, now what we have to realize is that since these zeros follow, they trail non-zero digits and they're to the right of the decimal point, they are significant. And that does not match these zeros, because these zeros are not to the right of a decimal point, and therefore these, although mathematically these are the same thing, they are not insignificant figures. So in order to change that, we would have to realize that all these zeros are not significant because they are to the left of the decimal point, and therefore we have 2 significant figures. So we have to make sure that this has 2 significant figures as well. How can we do that? Well, and I'm running out of room here, but we can change this to 2.3 times 10 to the 6th. And now we're happy. Alright, with that being said, let's move on to significant figure rules with operations. So, in this case, we have really 2 rules that we follow, and they're easy to get mixed up. But once you have them down, they're pretty straightforward. So the first one is adding or subtracting. So the first thing we want to do is we want to add, find our problem. Let's add the numbers through. So in this case, 4 plus 3 is 7. Alright, that being said, now we want to round the sum or difference to match the same number of decimal places as the least number of decimal places added or subtracted. So let's bring this problem down and realize that that's 4.0 plus 3.00. Well, the first thing we have to do is realize that this has 2 decimal places, and this has 1 decimal place. Therefore, since 1 is the smaller amount of decimal places, our sum is going to have 1 as well. So we have 7.0 should be the correct answer with the correct number of significant figures. And the same thing goes with subtracting. So if I were to take 4.0 minus 3.00, well, we would realize that 4 minus 3 is 1, but we have 1 decimal place here, we have 2 here, and therefore we have 1.0 should be the correct number of significant figures. So decimal places are most important when we're adding or subtracting. With that being said, multiplying or dividing is similar but not quite the same. With multiplying or dividing, we want to take the smallest number of significant figures that were multiplied or divided and apply that instead of decimal points. So let's take an example. If I were to say 6.0 times, let's say 6.0 times 3.000. Well, 6 times 3 is 18. And then we have to realize that in this case, instead of the decimal points, we realize that there are 2 significant figures. And just as a review, because this 0 leads non-zero digits and it's to the right of the decimal point, and this one has 4 significant figures because these 3 zeros are to the right of a decimal point, and all of these zeros trail a non-zero digit, and therefore this 6.0 has 2 significant figures, this 3.000 has 4 significant figures, and therefore we want this 18 to have the same number as the smallest amount of significant figures as we have multiplied, and that would be 2 significant figures. Let's use something a little bit nicer. Yeah, there we go. 2 significant figures. And so we have to realize that 18 That's two non-zero digits that are both significant, and therefore we do not have to even worry about adding a decimal point. Sometimes you'll see a decimal point added just to emphasize significant figures, but that is generally not necessary. But with that being said, let's move on to division, and it's the same rules. So we'll say division, same rules, and let's use the same problem, 6.0, just dividing them. 6.0 divided by 3.000. Well, in this case, as we discussed before, this 6.0 has two significant figures. This 3.000 has four significant figures, and therefore we're going to realize that, well, when we divide them, we get 2, but we want two significant figures. 2 by itself is just one significant figure, so we have to add a decimal point and a point 0. This 0 is to the right of the decimal point, and it trails a non-zero zero digit, and therefore we have two significant figures in the quotient. So that is how we are able to distinct between the two. And just as a final note, so that there is no confusion, when we add or subtract, we are concerned with the number of decimal points and not total significant figures. However, when we multiply or divide, we don't care as much as the decimal point as much as how that changes the significant figure. So it's always the lower of the two. It's always the lower. You can remember that, but you want to be able to realize that adding and subtracting, it's the lower amount of decimal places, and with multiplying or dividing, it is the lower amount of significant figures. With that being said, this is the end of my first video lecture, and I hope you guys enjoyed it. If you did, please leave a like and subscribe. Thanks.